We're going to consider a car moving from 10 meters per second to 30 meters per second in 5 seconds. We're going to determine we're going to figure out what can be determined from that information. Well, that information, and of course I've gone a little further in this diagram than just that, but that information is right here. We know the initial velocity, the final velocity, and the delta t of the car, respectively 10 meters per second, 30 meters per second, and 5 seconds. So what can we determine if we know V0, Vf, and delta t? Well, from V0 and delta t we can't determine anything. From Vf and delta t we can't determine anything. Now from V0 and Vf we can put those together in a certain way and use delta t, but I want to figure out what we can figure by just combining two elements at a time. So if we combine V0 and Vf, what can we get by combining V0 and Vf? Well, we can get the average velocity. We can add the initial and the final, get the average. In this case, it would be 10 meters per second, 30 meters per second adds up to 40 meters per second. Half that is 20 meters per second, and that's clearly halfway between these. That's clearly the average. Okay, we can also get delta V, the change in velocity, which is something we would want to use if we were going to determine, say, the acceleration. Okay, so we get the average velocity and the change in velocity. Now that we have the average velocity, the change in velocity, and these quantities, and I draw a circle around that, except this whole thing is going to get so messy we won't be able to figure out what anything is. But if we do that, from delta V, V bar, and the three given quantities, what can we do? Well, we've got delta T sitting over here. We can pair that up with V bar and get delta S. Not only that, but we can pair delta T up with delta V and get the acceleration. Okay, if we multiply the average velocity by the time interval, we get the displacement. If we multiply the change, or divide the change in velocity by the time interval, or change in clock time, we get the acceleration. So now we have 1, 2, 3, 4, 5, 6, 7, all 7 of the quantities in terms of which we can think about uniformly accelerated motion. Well, I add a question onto this, but right here, again, not going to circle it, but I could circle just this much, and I'd have a complete analysis of the uniformly accelerated motion, and also, again, without ever having had to resort to the equations. That would be really informative then to go to the equations and see what the equations tell us about this and reconcile that with what our reasoning tells us. Because having reasoned this out, we understand every part of the problem, but we also have to understand how to use the equations. So I recommend that we do that. Okay, now, if the car mass is 2,000 kilograms, now what can we find? Well, it didn't take long. I threw the mass up here because now we have the mass. Very quickly got the response that, well, we put the mass with the acceleration, we get the net force. Okay, so that's very clear. Now, what do we know if we have mass, net force, and acceleration, and all this other stuff? What can we put the new quantities with? Is there anything else we could put the mass with? Doesn't appear to be, but let's keep our minds open. Okay, is there anything else we can put the net force with here to determine something else? Net force and delta V, net force and V bar. What about net force and delta S? Aha, net force multiplied by the displacement is what? It's the work done by the net force. And as we've seen, the work done by the net force is equal to the change in the kinetic energy of the object. So if we have the car mass, we can use that with the acceleration to find the net force. The net force will go together with the displacement to give us the work done by the net force, and that gives us our change in kinetic energy. Anything else? Well, somebody brought this up, and actually didn't actually say average power by the net force, said horsepower. Well, that's good enough. Okay, horsepower is a measure of power, and we didn't have a horse handy, so we have to go to the abstract definition, which is just the average power by the net force is the work done by the net force divided by the change in the clock time. Okay, and that's the average rate at which the amount of work done up to a point, it changes with respect to clock time. It's another rate calculation. So that's something else we can determine. Now there's even more. Okay? If we put the mass together with the initial velocity, we can get the initial kinetic energy, just 1/2 mv0 squared. Now the lines kind of get fuzzy here, but here's a line from V0 down to the kinetic energy, initial kinetic energy, and a line from the mass down to the initial kinetic energy. Now if we put M together with VF, well, I had to snake a line down to KE sub F and another one weaving through here to get the final kinetic energy. But M and VF do give us KEF, the final kinetic energy. Now that we know the initial and final kinetic energy, what can we do? We can put those together to get the change in kinetic energy. And, well, think about it. Now that's something we just saw over here. So we have two different ways to get the change in kinetic energy, and they have to agree. All these connections weave these things together in a way that the change in kinetic energy has to be the same one way as the other. And that goes back, of course, to the way we've defined kinetic energy and the change in kinetic energy in terms of substituting A equals F over M into the fourth equation of uniformly accelerated motion. One says VF squared equals V0 squared plus 2A delta S. We do that, and our F net delta S comes right out. And our 1/2 mv0 squared, 1/2 mvf squared appear on the other side in the way that establishes the work kinetic energy theorem. So, just a quick synopsis. We, of course, spent 2-3 times as long discussing this in class and bringing out these ideas because that's the really essential process.